Yeah, so ours are not going back until September.
Yeah, I mean, they've started going back to school, but the summer holidays start in a week anyway. So it's
Right. So it's yeah.
we have another 6 weeks.
Mhm.
Yeah, well, yeah, in the US they start like in the end of June, but we have some summer camps going, so
Okay.
the
Okay.
kids
Oh,
are.
okay.
But it was extremely hard to get into those camps because they made the space much more limited because they want
Right.
small groups.
Mhm.
Okay, so I need to collect my
Okay.
notes.
Yeah. Okay. Right. Let me start by sharing the screen.
Yes, yeah.
Oops.
Okay,
No,
great.
there we are.
Mhm.
Right. Okay. So it's my pleasure to welcome everybody to today's Lagoon seminar. Our speaker today is Sasha Polichuk, but before I formally introduce him, let me announce next week's seminar. So next week we will be back at our usual time from 1 to 2 o'clock, and the speaker is Markus Reinecke, who will speak on Fano Quiver Moduli. But it is my pleasure to announce today's speaker, if my screen works. Sasha Polichuk from the University of Oregon, who is going to tell us about the geometry of the associative Young-Baxter equation. Thank you.
Okay, great. So yeah, thank you very much for inviting me, and I hope you don't mind the change in time that makes it possible to people in the US. Okay, I'll start sharing my screen now, so I could give a talk. Let's see. All right, here we go. Yep. Okay, so this talk is about associative Young-Baxter equation. So first, let me present this equation and all the kind of related equations where the motivation comes from. So on this page, obviously, there's no geometry, just some algebraic formulas. But nevertheless, let me remind you some of the meaning of what is going on here. So the story begins with actually two other equations: classical Young-Baxter equation, quantum Young-Baxter equation, which are both parts of the theory of quantum groups. And I won't go much into this. So let me just say that so in classical Young-Baxter equation, so you have this function r of v, which is a meromorphic function, and it takes values in G tensor G, where G is some, let's say, Lie algebra over complex numbers. So when I write R12, so all these symbols, they have the meaning that you take R13, etc. So this is taking place in triple tensor product. So you take something like R tensor 1. Now there's obviously no 1 in the Lie algebra, so this means that you're actually sitting inside the triple tensor product of the enveloping algebra. Right, and so that's how you understand this equation, and the brackets are just the Lie brackets. For quantum Young-Baxter equation, this takes place in so the big R. So well, lives in some associative algebra, well, tensor squared, and so yeah, I guess the typical case is when A is just a matrix algebra. And so the classical Young-Baxter equation is obtained as some kind of semi-classical approximation. So when you expand the quantum Young-Baxter equation and kind of differentiate it, so the first approximation, you get the classical Young-Baxter. So the associative Young-Baxter equation, so it looks actually rather similar to the classical one. So you see that it has also 3 terms, and there are 3 quadratic terms. But instead of brackets, it has tensor product. It has just the product, and so the tensor is again takes values in A tensor A, where A is an associative algebra. So it's some kind of associative analog of this Lie kind of theoretic equation. But strangely enough, it has connection both to classical, kind of quite direct connection both to classical and quantum equations. So you can kind of, so when you have a solution of associative equation, you can sometimes get solution of classical, and sometimes it also satisfies quantum Young-Baxter equation after you just scale it somehow. So anyway, so it's a maybe a rather strange equation, but so my point is that it has some interesting geometry, and maybe kind of understanding the geometric meaning of this is a step to also understanding kind of more geometry behind quantum Young-Baxter equation, which would be great. Okay, so actually this is probably going to be the last time you see these equations. So in the rest of the talk, yeah, so take a good look, because in the rest of the talk, I'm just going to write AYBE instead of writing this equation. Yeah, this is a question. Is R in the quantum case invertible? Yes, so it is invertible, but in the last case, it is not. Oh, okay, actually, it's totally fine to send questions by Zoom. I do see them. Yes, so in the quantum case, R, big capital R is invertible. In the classical and associative case, little r is not invertible. So in fact, there is a extra condition which is called unitarity in the classical case, and so it's there's some kind of, it looks more like a skew symmetry in the associative case. So when you switch the order of factors, then you should get minus r of minus u minus v, something like this. Right. So let me say also that there is a classification of solutions of classical Young-Baxter equation. Okay, so maybe we had enough look at these equations. So they look actually maybe a little intimidating. So let's go to next page. So first, for classical Young-Baxter equation, the story is the following. So Belavin Drinfeld classified, so yeah, they made some theory of solutions, classified solutions. So well, they classified so-called non-degenerate solutions. This means that this tensor has to, which is depends on a parameter. So for generic parameter, we want this tensor to be non-degenerate. So they come in three families. So reflecting the character of the functions involved. So there are elliptic solutions, trigonometric solutions, and rational solutions. So that's kind of the nature of dependence on the parameter v. So okay, maybe let's look once more. So there is this parameter v in the equation. So so in the first case you get elliptic functions of this parameter. In the second, it will be polynomials of the exponential, and in the last one, it's just rational functions. And furthermore, they classified all elliptic solutions, and they classified also all trigonometric solutions. And so elliptic solutions exist only for, okay, so sorry, this is all of this for simple Lie algebra G. So elliptic solutions exist only for SLN. So, and trigonometric are actually kind of the most interesting part for me, because they depend on some combinatorial structure called Belavin-Drinfeld triples. So basically what happens is that from this trigonometric solution, you automatically get an automorphism. So A is so this G comes with an automorphism, and so you view this automorphism up to, okay, let's call it maybe sigma. So there is an automorphism of G. And then so you in this in the corresponding class up to inner automorphisms, you find Coxeter automorphism, and so then there is the corresponding, so this pair group an algebra with automorphisms gives rise to Dynkin diagram, which kind of looks like so for example for yeah, so and then the data that you have is that there will be some pairs of, so there will be two subsets of simple roots, kind of, and some automorphism, sorry, some bijection between them, which preserves scalar product, preserves inner product. And then, so basically the solution depends on this data plus some continuous datum, which is something entirely, some tensor in tensor square of the Cartan subalgebra. But now my point is that so there is a similar classification in the case of associative Young-Baxter equation. So there is a similar classification, and all elliptic solutions are basically kind of in bijection with elliptic solutions of classical Young-Baxter equations. So the solution of elliptic solution of classical Young-Baxter are all obtained as limits of associative one. And for trigonometric solutions, there is also some combinatorial data, so which I called, so for trigonometry, so of course here what I need to do is I need the conditions similar to the fact that here we consider only simple algebra. So we consider this for the matrix algebra. Okay, so take n by n matrix algebra over complex numbers. So it means that our tensor R will live in tensor square of matrix algebra with itself. Okay, so all right. So what are the trigonometric? So what is the combinatorial data? So I call it Belavin-Drinfeld associative Belavin-Drinfeld data. So this consists of a pair of cyclic permutations sigma naught and sigma, and then I can see, so okay, so the first permutation actually you can make standard, so they should be in Sn, and so everything is up to conjugation by permutation, so I can assume that sigma naught is a standard one, so sigma naught of I is just I plus 1. And then kind of the analog of simple roots here is the graph of sigma naught. So this is pairs I plus 1, where I goes from 1 to n in z mod n. And so then the subsets gamma 1 and gamma 2 are going to be proper subsets here. And the condition is that if you now act by sigma times sigma, so this acts on pairs. So it does not have to preserve. It does not preserve the graph of sigma naught unless sigma and sigma naught commute. But the condition is that it sends gamma 1 to gamma 2. And so then I call by tau the induced bijection. So tau is really this. So it's induced by sigma times sigma. All right, so you see that this is a little bit similar to Belavin-Drinfeld triples, but there is this condition that the bijection, it has to be induced by another cyclic permutation. So that's kind of crucial part of this data. And so there is no continuous parameter, unlike in the classical case. And the claim is that this data precisely gives you, so each such data gives you a solution of the associative Young-Baxter equation. And this is complete classification. So actually, I prepared one more formula, and I promise that there will be no more. Okay, where is it? Okay, here it is. So this is actually the solution corresponding to the Belavin-Drinfeld associative Belavin-Drinfeld data. So we have, yeah, unfortunately notation is different because I took it from another paper. So sigma naught is what C naught is what I called sigma naught, and C is what I called sigma. So I'm going to change notation because C will be a curve, so, because we'll be talking about geometry. So yeah, this seems to be absolutely no geometry in this equation, but strangely enough, in our work with Jan Kilikili, we actually interpreted this. Every term of this formula has a geometric interpretation. So it's actually, yeah, maybe I'll mention this later. So in fact, they all count some symplectic areas. So this has an interpretation from the point of view of Fukaya category. But my talk today will be about the kind of B side, about different type of geometry. So it will be more algebraic geometry related to this to these equations. So right. So so I'm going to explain now. Okay. So again, this formula is a bit intimidating. So let's just look at some geometry now. So what is the geometric? How this construction arises geometrically? So there's a geometric construction of solutions, and that's kind of basically will be the main focus for me. So I can forget about the equation itself now. So yeah, so there's a simple example how this appears, and then this example can be generalized. So the example is the following. So let's start with some, yeah, so let's start with elliptic curve. So C will be elliptic curve. And now let's fix some degree and rank and consider modular space of stable bundles on C of fixed rank and degree. And so this is again going to be another elliptic curve. So yeah, actually isomorphic to this one. So now you consider a pair of vector bundles. So V1, V2 will be kind of pair of points there. So pair of vector bundles. And on the other hand, let's also consider a pair of points. So this will be non-isomorphic. And then there's two different pairs of points. Two different, sorry, the pair of points, two different points. So so it is well known that for stable bundles, which are deformations one of another, you have, if they are not isomorphic, then actually you will get absolutely no x between them. So all x from V1 to V2 are going to be 0. So, well, namely hom and x1. And so what you can do now is you can consider the following sequence of three possible three composable arrows in the derived category of coherent shifts. So you can consider skyscraper at x1. So you can consider possible morphisms from v1 to ox1. So here there's, so if rank is r, so there is r-dimensional space. Then we have r-dimensional space of x1s from ox1 to v2, and then we again have r-dimensional space from v2 to ox2. So now this sequence of arrows, okay, so this is in derived category of coherent shifts of C. Or if you, yeah, if you want kind of to discuss this without mentioning derived categories, so we just consider composition home tensor x1 tensor home. Okay, so well, there is no such composition, but there is actually what is called massive product. So let's call this massive product. So how is it? Yeah. So the main point here is that any pair of these arrows has zero compositions simply because there are no x1 from v1 to v2 or from ox1 to ox2. So so what you can do now, if you calculate these homes in x in by some complexes, right? So you can choose complexes which are multiplicative. So then basically you'll have the following setup. So these morphisms will be represented by some classes. So you'll have some A1, A2, A3 here. And so we actually represent them by some cochains, sorry, by some cocycles. So A2 is actually cocycle here. And so when I consider the product, so A1, A2 is zero in cohomology. So it means that it's going to be differential of something. And A2, A3 is zero in cohomology. So it's also going to be differential of something. And so then you can consider the class of A12 times A3 minus A1 times A23. So this is called, so the class of this cohomology class is called the massive product. And it lives in home from the very first to the very last, ox2. And it turns out that this does not depend on any choices. So in principle, it could depend. If I had home from v1 to v2, then I could choose a12 differently. I could add to a12 some cocycle in degree 0, but because there are no such, so I actually have no. So this is going to be univalued massive product. Okay, so in fact, it's important for me that this structure, which in general is only partially defined, so it can be extended to so-called infinity structure. On the entire category, or maybe on the subcategory with these objects. So this means that we have a system kind of not only double products, but also triple products, quadruple products, and so on, satisfying kind of higher axioms, kind of associativity up to homotopy and so on. So plus some higher associativity axioms. And this massive product will actually be nothing, but it will be part of M3. So, and because of this, so when you look at these high associativity axioms, they give us some equations for this M3. So the equations might look like this. So you have, if you have 5 elements, So you can take M1 of A1, A2, and then you stick another M3 in between. Right, and then you can do this in 3 ways. So you can also stick M3 in the middle, and you can stick M3 in the beginning. And so you have actually 3 terms, like in our Young-Baxter equation. And it turns out that actually looking at this massive product, you actually get a solution of associative Young-Baxter equation. So this has to be a little bit explained. So what has to be explained? So this map I have to dualize to get a tensor where I need it. So basically all of this, so here I have tensor product of 3 r-dimensional spaces on the left and 1 r-dimensional space on the right. So I have to use duality, Serre duality. So x1 or x1 v2 is dual to home v2 or x1, so I can actually move it to the right side, and I'll get tensor of kind of 2 spaces, home from v1 or x1, home v2 or x2, and on the right I'll have 2 similar spaces but with points switched. So actually, if you trivialize all these spaces, so kind of identify them all with the same space, so you'll just get a map of the type v tensor v to v tensor v, so which is the same thing as so this will be r. So which is the same thing as an element in end v tensor end v. So the only thing that is different here from the equation that I showed in the beginning is that there are more parameters. So the tensor in my first version of the equation depended on just 2 variables. So here there are 4 parameters. There is x1, x2, and there are 2 parameters v1 and v2. So in fact here these are both pairs are live on elliptic curve, so it can be arranged to depend just on differences. So by carefully choosing, so if this depends only on differences, then we get precisely the equation in the beginning. And so this can be arranged, but kind of more importantly, instead of arranging this, you can also consider the version of the associative Young-Baxter equation, which depends on 4 parameters, and where you don't need to add variables, so you can just kind of view them somehow set theoretically. You just you just have a more complicated equation for r and 4 parameters. Okay, so this construction actually can be generalized. And it is clear here that we're really not using, yeah, by the way, the claim is that in this way you get elliptic solution. So we started with elliptic curve, so it's not surprise that we get elliptic solution. And so one kind of obvious idea is that you can try to apply the same to, instead of elliptic curve, you can take its degeneration, some nodal curve of arithmetic genus 1, and say take some bundles on it and play the same game. So you will get some trigonometric solutions, but sadly not all. So if you play the same game with degenerate curves, you do not get all trigonometric solutions, and somehow this is the puzzle that I'm going to explain how to solve today. So it turns out that you have to go into some non-commutative sheaves of algebras in order to find all solutions. Okay, so this construction can be generalized. So generalization. So you do not really need to start with a curve. So you can start with any pair of objects which look like which have kind of x like vector bundles on elliptic curves. So such objects are called one spherical objects. So with a pair EF of one spherical objects. So this means that in some category or infinity category. So this means that when you consider the X algebra from E to E, so you'll just have kind of field in degree 0 and field in degree 1 and nothing else, plus some technical condition on homes from other objects to E. But so I also want that when I consider when I consider X from E to F, that they all live in degree 0. So there is only home 0 from E to F, and this is some n-dimensional space. And there are no homes in other degrees. So then when you consider X1 from F to E, kind of by the condition that they're spherical, this is going to be a dual space. Okay, so and then what happens is that so the spherical object has one-dimensional X1 and no X2. So it means that you actually have deformations. So you have one parameter family of infinitesimal of deformations of this object. So you kind of so instead of this pairs of vector bundles and pairs of points, you can now kind of replace this modular space M that I had before by sort of deformations of E, and so the points I also replace by deformations of F, and so then I can still consider kind of same story. I can sort of deform E a little bit and consider kind of the corresponding massive product. So the same massive products may make sense. And this gives, well, okay, these are really formal deformations. So from this we get a formal solution. So it will be R depending on 4 parameters, x1, x2, y1, y2. So this will live in mat n tensor mat n, but then it depends on this x1, x2, y1, y2, which I should view as formal variables. So in fact, what happens is that this looks like so. So it starts with some singular terms, 1 tensor 1 over, so x2, yeah, so x2, x1, y1, y2 are just formal variables. So here there is some standard permutation matrix P. And then there is a regular part, which is a power series in all the variables. And so you can formulate the associative Young-Baxter equation for these things. So P is the permutation matrix, sorry, tensor. So it's some EIJ, EJI. Right, so it's a formal solution of the associative Young-Baxter equation. Okay, and so the theorem that we proved jointly with Jan Kilikili is that in fact this formal solution of associative Young-Baxter equation, actually it carries all the information about this pair of spherical objects. So it actually remembers everything about them. So the entire A infinity structure kind of encoded is encoded in this solution. So this gives kind of, so I'll kind of formulate it roughly. So this gives kind of equivalence so if you have okay, so I'll start doing slightly more precise. So you have to consider cyclic infinity categories generated by pair of spherical objects as above. Kind of one spherical with only homes from left to right, from E to F, and formal solutions of the Young-Baxter, of the associative Young-Baxter equation up to some equivalence. So here also there is, so there are some equivalences for on the left and on the right here. Okay, so now okay, any questions up to this point? So next I'm going to move towards non-commutative orders. So it's a good place to stop and hear whether there are any questions.
Hello.
Yep.
Could you say a bit about how you get the higher A infinity products?
So they all recorded. They all recorded as part of this. Okay, so what happens is that so when you consider this massive product between deformed objects, it somehow reflects the higher products between original objects. So this is kind of the formally this happens by playing with twisted complexes. You realize these deformations by twisted complexes, and that's how they appear. But more formally, what happens is that when you look at the terms of the expansion in the power series, then the terms with higher powers, they record all kind of coefficients of all higher products, or at least enough up to cyclic symmetry so that everything is recovered. Okay, so basically, so how can you get a higher product? You can go from E to itself many times by x1. Then you can go to F. Then you can go from F to itself many times. Then you can go back to E, and then again to itself, from E to itself many times. Then go back to F, and then again from F to itself many times. So there is 4 integer numbers involved, and these 4 integer numbers are powers of x1, x2, y1, y2. So it's kind of like a generating. So this solution of the associative Young-Baxter, it's kind of like a generating series for the coefficients of higher products. Okay, I hope.
Hi, can I ask a question?
Yes.
So in this theorem, if you start with the cyclic infinity category, that's equivalent, if I'm not mistaken, to some infinity category with the compatible Calabi-Yau structure of some sort?
Well, maybe, yeah, it depends on what you mean by, yeah, I think so, yeah.
I see. Do you know if there's any sort of picture of what that looks like in terms of the solutions of the Yang-Baxter equation?
Sorry, what looks like?
The interpretation of this pairing in the cyclic infinity category as a Calabi-Yau structure.
Yeah, this is all happening on the left here, so I don't
see.
understand. Yeah.
My question is if there's anything on the right that's
no, there's nothing on the right. So what happens is that somehow cyclicity allows you to recover some infinity products from other infinity products, and so it kind of it allows you to record it in this way. So if you have non-cyclic infinity structure, it won't be there will be no right side. It won't be possible to write it in this form, to kind of record it in this form.
I see.
Or maybe if there is a generalization, you would have to, at least you would have to consider maybe several tensors like this with some more equations. I don't know. Okay, so let me now.
May I ask a question, please?
Yes.
Hi. some 15 years ago, there was a paper by Travis Shedler who gave solutions to the associative Young-Box equation for. There was a correspondence between with Belawin triples for GLN. So my question is, does your approach, does your classification give anything new?
Yes. My approach was precisely based on Travis's paper. So this was also many years ago when I did this. This was all kind of, this question is back about classification of trigonometric solutions and stuff like that. So I actually precisely generalized Travis's work. So I kind of completed it. So he only considered some trigonometric solutions. He showed when trigonometric, so he considered this for he asked which solutions of the classical Young-Baxter equations for SLN can be extended to associative Young-Baxter, and I more generally classified all trigonometric solutions of the associative Young-Baxter.
Okay, can you give an idea as to how many more solutions can you get as compared to those by Travis?
Sorry, so I precisely explained. So they're obtained by yeah, I forget now whether he actually already yeah, I forget now. I think he had some restrictions compared to my picture. So in my picture, I consider arbitrary pair of permutation. So there's two cyclic permutations and some subsets. I think I think he had some further restrictions.
Yeah. So the question will be: have you got a classification of those cyclic permutations? Because so far I understand your result as theoretical. So my question is, can we see it?
What do you mean? So there's no restrictions. So there could be arbitrary permutations. So what kind of classifications do you mean?
So
arbitrary cyclic permutations.
And no restrictions.
No restrictions whatsoever on them. No.
Okay.
Oops, sorry. I think we've been talking too long, so my iPad decided it's time to shut down. How do I restart it? Start broadcast. Okay, back. Okay, so let me proceed to a little more geometry. Otherwise, I will never end on time. So. Yeah, so we can discuss more maybe after the talk. So, okay, so let me now say how non-commutative orders appear. So, so when you have, okay, so first let me explain. So what do I mean by this? So suppose C is some integral projective curve. So omega C is the dualizing sheaf. It's not necessarily line bundle because C can be singular. So now I consider the so A. This will be an order. So this means that this is a coherent sheaf of all algebras. And generically, it's just a matrix algebra. Okay, for simplicity, let's work over C. So, so generically, this is just a matrix algebra over functions on C, but it may have some degenerations. So now I'm making the following definition. So I say that A. Yeah. So generic. So this was a definition of order. So now. I say that A is a symmetric spherical order if the following holds. So if in addition it has only one-dimensional H naught, so only constants. Sorry, one, and there is so there is a morphism of coherent sheaves. Okay, so or linear morphism such that it induces a perfect pairing. So A tensor A goes to omega C is perfect and symmetric. So perfect symmetric pairing. So so what does it mean that it's perfect? So A here is not a vector bundle, so this has to be explained. So perfect means that a map from A to home to sheaf home from A to omega C is an isomorphism. Okay, so it turns out that this is equivalent to the condition that when I consider the A as a module over itself, so if I consider it as a object in the perfect category, so the category of A modules generated by kind of locally projective ones, so then A is actually perfect. A is one spherical. So if in addition we have for some point, for some smooth point, okay, so C is singular, but let's take some smooth point P. And suppose that A splits over this point, so it's you just get a matrix algebra when you restrict it. So then we can consider, so we can view V tensor OP as a module over A. So this is kind of an analog of skyscraper, but this is an A module. So and so then it turns out that this pair A V tensor OP, this is a pair of one spherical objects generating the perfect category, and so in particular, from what I said before, it actually produces a solution of the associative Young-Baxter equation. And so now, okay, the main claim is that actually all, okay, so this is false as stated, but this is kind of morally, so all formal solutions actually come from this. Come from some, okay, so this is a theorem actually. Come from some pair C and some one spherical order. Sorry, so from some spherical non-commutative order. So this may, yeah, so this is not true as stated, because in order for this to be true, you have to allow C to be a sticky curve. So should allow to be sticky, but let's ignore this for now, because so in all examples I'm going to consider, C will be usual curve. So for example, if you take C to be elliptic curve, and you can take A to be just endomorphism bundle of some stable vector bundle. So then from this you get elliptic solutions. Right, but it turns out that in order to get all trigonometric solutions, it's not enough. So the main point, it's not enough to consider only locally free orders. So you have to allow A to degenerate somehow. Okay, so right, so okay, so how do you construct orders? So here is let me now explain how to construct such orders, such non-commutative orders on Okay, so let's just take the simplest degeneration of elliptic curve. So we'll take C to be irreducible nodal curve of arithmetic genus 1. So this curve is obtained by taking P1, so it has normalization map from P1, and then we just glue together 0 and infinity. So they both go to the node. So here is a possible construction. So you start with the following data. So start with I. So I will be a subalgebra in direct sum of two matrix algebras. So, and it's going to be a maximal isotropic subalgebra. So what does it mean? So you have, so on direct sum of two matrix algebras, I can consider the following pairing. So if I have, okay, this is algebra itself. So for A, B in this direct sum of two matrix algebras, I can consider the pairing given by super trace of A times B, where I kind of think of first component as even and second as odd, and I have the super trace. So there's a super trace to see. Okay, so we consider maximal isotropic subalgebra with 1. Yes, it has to contain 1. And so so it's equivalent just to say that it has dimension n square, and the super trace on I is 0. Okay, so from this we get to order. So we get order A. Yeah, sorry, there's one more data. So in addition, let's fix also V, some vector bundle on P1. Okay, so every vector bundle on P1 is just sum of line bundles. And we trivialize it, trivialize fibers at 0 and infinity. And so then from this data, we get some order on C. So I'll call it A of VI. So it's going to be a subsheaf of the push forward of endomorphisms of V. And so basically we'll just impose some condition. So when I look at the fiber at 0, so there I have, so this will be sections such that when I look at pair A of 0, A at infinity, then this pair, this is going to be a pair of matrices because we trivialized V. So this has to lie in our isotropic subalgebra. Okay, so and then the claim is that if this order has only constant global sections, then this order is symmetric spherical. And in fact, all symmetric spherical orders on C, on this irreducible nodal curve, are obtained, are of this form. And furthermore, we can V has to be tilting, so it has to be only direct sum of some number of O's and some number of ones. And the main theorem is that So there is a construction starting from associative Belavin-Drinfeld data. So starting from this sigma naught, sigma, and gamma 1, gamma 2. So we produce this isotropic subalgebra such that, and V also, such that the corresponding order precisely gives corresponding trigonometric solution. Of the associative Yang-Baxter equation. So, okay, so I should finish soon. So let me just add the remark that so this gives a geometric realization of all trigonometric solutions using non-commutative orders on this nodal curve. So before with Yang-Killikili, we constructed a different realization using Fukaya category of some square-tiled surface, which is kind of obtained as a covering of a torus. But so maybe the symplectic construction has the advantage that that every term in the formula for solution actually had some geometric interpretations. It corresponded to various holomorphic disks, but nevertheless, kind of comparing this theorem with that result, it means that there is actually some kind of homological mirror symmetry going on. So these orders with so there's some equivalence of orders of the categories of modules of associated with these orders, with at least some full subcategories of Fukaya category and possibly with entire Fukaya category, depending on whether there is a corresponding generation result. Okay, so yeah, maybe I'll give one simple example and we'll stop there. So one simple example. So suppose, so this sets gamma 1, gamma 2 can be empty. So suppose gamma 1, gamma 2 are empty. So then the corresponding right, so then the corresponding isotropic subalgebra is the following. So let's consider, yeah, so okay, so this has to be like this. So E sits in mat n times plus mat n, so it's pairs. So this will be pairs of matrices such that A1 is upper triangular, A2 is lower triangular, and if you take diagonal part of A1 and diagonal part of A2, they are not equal, but one is obtained from another by cyclic permutation, sigma. So of course, yeah, so sigma naught I'm taking to be the standard cyclic permutation. That kind of determines that we're talking about this standard barrels. Yeah, so and for the general case, you have to kind of generalize this construction. You have to define certain parabolic subgroups, and then the sigma will act on kind of their Levy, their kind of semi-simple parts. It will kind of permute the semi-simple parts. So there will be some. It's actually a pretty explicit construction, which is in my paper on the archive. All right, so I'll stop here. So unfortunately I didn't have time to talk about the Lie case, but the Lie case is more well known, and so my only contribution was that in the Lie case I found the sheaves of Lie algebras on these irreducible nodal curves, which produce the Belavin-Drinfeld trigonometric solutions. All right, thank you very much.
Thank you very much. Let's all thank Sasha for this beautiful talk. Okay, yeah, so virtual clapping. Are there any questions? If you have questions, you can either put them in the chat or unmute yourself and ask them.
I had one. Hello?
Yeah.
In the last slide, when you write in the claim that you have the order form V is O plus R plus O1 plus N minus R. What is the R again? I got lost with
yeah,
rank?
you can't predict, so it depends on the so basically you have to split it into two, yeah, in some way. Yeah, I can't say in which way. Yeah, so
is some kind of rank of some bundle, or
no, sorry, no, this is just no, it's not a rank of some bundle. Sorry, no, you just derive that V has to be tilting, so it should have no high X to itself, and that's the only way that this can happen.
And the genus of the curve doesn't play a role at all, right? Or does it come in somewhere?
So the curve is arithmetic genus 1. No, the curve is fixed. It's all for this fixed irreducible nodal curve. No, that's the whole point. So before, when I tried to, when you try to construct trigonometric solutions, in principle, you can try different degenerations of elliptic curve. They all be arithmetic genus 1, but there are also, there are also these wheels of P1s. So it turns out you don't need to consider them. So all you need is just this irreducible nodal curve and appropriate orders over it. And this already gives you all solutions.
Okay.
So, but in particular, it means that, for example, it means the following: that if you take this wheel of nodal curves and you take your favorite stable bundle over it, then there's going to be some order over irreducible nodal curve somehow attached to it, and yeah, because they both kind of give rise to trigonometric solutions. And I suspect that what happens is that if you take a stable bundle here, so the corresponding order is obtained as follows: you take endomorphisms of this bundle, and then you collapse this wheel to the irreducible curve. You collapse all the components to the node, except for one, and then this will give you one of the orders like this.
Thank you.
Does anybody else have a question? Well, maybe while we wait, I can ask a question. Is this related at all to the non-commutative nodal curves in the work of Boban and Drost?
Yeah, well, I think these are examples of, yeah, so I think this, well, maybe not all, no, actually, I'm not totally sure, but I think some of them must be examples of them.
Because,
yeah, I don't, yeah, I think the definition is quite technical, so I did not check whether they satisfy, but indeed it's somehow, it's very close in spirit, because in spirit what they want is that they want to have some non-commutative geometry which will be like nodal curves, and right, and so this indeed this non-commutative order over irreducible nodal curve, it's somehow, it is like other nodal curves. So I don't know whether there is a precise connection, but I think this certainly deserves to be studied. I think it's very possible that it is a nodal order.
Because somehow when they then also get a connection with the derived category of some finite dimensional algebra. And
yes, yeah, that's true.
Somehow,
yeah, this is actually not surprising from this point of view, because there is because yeah, I think I understand now. Yeah, so yeah, so basically yeah, I don't remember in the paper what is the connection to some other algebra, but okay, so so there is some connection to gentle algebras. So but in order to do this, you need to first consider some non-commutative resolution, because this order by itself is still kind of not non-smooth in non-commutative sense. But you can do kind of similar thing as what they do. So there's some kind of analog of Auslander type resolution for this category, and that category should be equivalent to some partially wrapped Fukaya category, and those are usually described by gentle algebras.
Mm-hmm. So this curve you described, so when you look at the homological mirror, you would expect it to be described by some gentle algebra.
The partially wrapped Fukaya. So
Yes,
this category by itself corresponds to just fully wrapped or either fully wrapped
because
or
it's a perfect category.
well, sorry. So perfect response to compact Fukaya. If you consider derived category of all kind of the entire bounded category, it should correspond to fully wrapped. But both of those they're not described. So they're not described by gentle algebras. So in order to do this, you need to add stops.
Yes.
And so adding stops corresponds to finding non-commutative resolution here. And I think this is possible.
I see. Okay, thank you. Are there any other questions?
I mean, maybe this is kind of related to the last question, but can you think, instead of changing the order, is it possible to think that there's a single CY1 category and you're just picking different pairs of one spherical objects in it? Like, is there a spherical Crepin resolution of this curve, and your orders are just picking out different one spherical objects?
Okay, sorry. So again, you imagine that there is some big category in which they all live, but I mean, why not just take direct sum of all these categories? I'm not sure I understand. So if they don't generate, then what kind of relation you expect between different objects?
I mean, for the smooth elliptic curve, you get it in two different ways, right? You could either
yeah. For smooth
pick a
elliptic
vector
curve,
bundle.
Yes, that's
and a
right.
point. Or you said use the vector bundle to build in algebra, and then you pick the algebra. But for the one, you kind of didn't say it the first way. So I wonder if it can be said that way.
Yeah, I don't know. That's a good question. So indeed, the underlying curve is not changing, but I'm changing the order. Yes. Yeah, I think this might be related to the following fact. So if you consider the module, so you can actually consider modular space of all these things. So think about it as modular space of infinity structures, where you kind of fix this X algebra, where you have kind of two vertices and n arrows one way and n arrows in the other way in degree 1 and so forth. So you can fix all this data. Then there is a modular space. So I think what's different is that this modular space is not necessarily reducible. So it might have different components. So in other terms, so somehow, yeah, maybe this is not directly related to your question, but somehow, yeah, I'm just thinking that maybe there is kind of one category for each component or something like this. Yeah, so I don't know, but yeah, the fact that there's not one component, it's kind of related maybe to this fact that you cannot obtain all trigonometric solutions by just degenerating the elliptic one. So maybe it's slightly different issue, but maybe related. I don't know.
Okay. Are there any more questions? So I don't see any more questions. Well, then let's thank Sasha again, and then maybe there will be an opportunity to sort of directly ask questions. You know.
Yeah, I have about 10-15 minutes to chat.
Okay, excellent. Okay. Okay.
So you mentioned one of the slides before. I don't know if you could go back one slide where you, no, maybe a bit one before. I'm not sure. I don't know. maybe one more further. No, I don't see it. Just the one before the last one, I guess, but I'm not sure now if it was the right one. Yes, here in the theorem. So you said that they come from a pair C, A. Can you say exactly? You said should allow stacky. That just means you have a nodal curve here, or what exactly do you mean by this?
So yeah,
Yeah.
the stackiness is in a different place than the singularities. So it's kind of, so there is one. Actually, here I'm a little bit. So to tell the truth, I actually don't know a single example where the curve is actually sticky, but the way I prove it, I must allow it. So I don't know whether this actually happens. It might turn out, but what I'm allowing here is the following. So I'm allowing that there is a single there is a single sticky point which looks like kind of some b mu n inside the curve, and kind of the complement is already going to be a affine curve, possibly singular.
Okay.
So something like, and that's going to be kind of precisely the point where kind of the action happens. So I'm going to take the corresponding second spherical. So this is kind of replaces this point P.
Okay.
In the construction. Yeah, it's actually related to the following fact. So the way these orders arise, maybe I can explain a little bit. So I just didn't want to. So when you have this pair, so from this pair you can construct a certain non-commutative algebra in a more or less canonical way. So what you do is you take a spherical twist. So you construct a sequence of objects, you take spherical twist around F and you iterate it and apply to E. You get sequence of objects EI. So then you can consider the algebra home from E0 to EI, direct sum over all I. This becomes a graded algebra. And this graded algebra, well, it has some special element of degree 1. So it actually turns out to be a Riesz algebra of some filtered algebra. And furthermore, for this filtered algebra, I have some concrete description of the associated graded. And this filtered algebra has Gelfand-Kirov dimension 1. So, and this implies by some well-known theorems, Warfield small and Shelter, so that this A is actually finite over its center. And so that's where the curves comes from. So the center corresponds to functions on the curve, on the affine part of the curve. And the filtration allows you to projectivize, to kind of complete it. So the problem is that I do not know the size of the center a priori. So because I said that the graded quotient is fixed, so if I know that the graded quotient of the center gives precisely the same as the center of the graded quotient, so that it's kind of as large as possible, then this will not, then there would be no stackiness. But the problem is that in this theorem, I cannot control the size of the center. I just know that the algebra is finite over its center, but if the center is kind of smaller than expected, then the curve might become sticky. But I don't know whether this actually ever happens. So I know it does not happen in the case n equals 2. So when you take so you need at least n equals 3 or so higher.
Okay, thank you.
Mm-hmm.
Okay, I have to go. Thank you, Sasha.
All right. Good to see you, Ed.
Nice to see you.
Bye.
Bye.
Hi, Sasha. Let me ask a very unexpert question. Why in this associative Young-Baxter equation you have 4 parameters?
Okay, so yeah,
How
so
exactly, why it's called the associative? Can you briefly describe in diagrams?
so yeah, so to begin with, when we just look in the very first slide, so in the classical formulation, the classic, so where kind of we consider solutions depending on differences. So the usual Young-Baxter equation, there you have R depending on one spectral parameter, and for the associative one you have 2 parameters. So but then you have to write some sums, so this has to be complex numbers. So if you want to write more general equation, you replace each of these parameters by 2. So U replaced by pair of parameters and V is replaced by 2 parameters. So yeah, so they place slightly, yeah, so I don't know why this happens. So it's kind of natural from this categorical perspective that you have these 2 parameters. So in fact, when you consider, so when you go from associative solution to quantum, from associative equation to quantum, so sometimes you show that sometimes it happens that solution of the associative Young-Baxter is already a solution of quantum. So that in that case, basically you can fix the first kind of, this is true for any fixed U. So kind of so you fix the first parameter U here, and then it satisfies the quantum Young-Baxter with with respect to the second one, with respect to V.
Okay.
Yeah, but in some, yeah, so why somehow this associative data has an extra parameter? It's hard. Yeah, so maybe one more, yeah, maybe one more thing I can explain is this, that when when you compare associative solution with classical, so what happens is typically this, that this associative solution has form 1. When you expand it with respect to U, it starts with 1 tensor 1 over U, and then when you write it expansion
in terms of V.
In Laurent series in U, so then this constant term which depends only on V. So let's say A was the matrix algebra. So if you consider projection from matrix algebra to SLN. So then if you apply it to this constant term, then you get a solution of the classical Young-Baxter equation. So this will be a solution of classical. So somehow, indeed, you see we need this extra parameter. So the solution of the classical parameter somehow appears as the constant term of the expansion in U. But it turns out that in good cases, for example, in elliptic case or in trigonometric case, the solution of the associative Young-Baxter equation is completely determined by the corresponding solution of the classical Young-Baxter equation. So kind of under enough non-degeneracy condition, it turns out that there is really not more data. So somehow it seems like you add more data because you add higher terms, but they're determined by this R naught V.
I see. How about those sums, and how is that? And why is that called associative? So
it's called associative.
Compare with in the VOE, that's the Jacobian identity, which is both in a certain sense was also kind of formulating associativity. So I didn't know if you have any kind of analogy here.
I think the reason it's called associative is purely by comparing it with this classical equation. In the classical equation, you have brackets, you have Lie brackets. In the associative, you just replace Lie brackets by product. So you kind of replace
Okay.
Lie operand by class, but it's also kind of manifest. It seems that indeed there is a good reason to think of it as an analog of the classical Young-Baxter equation in the associative world, because in this there is this complete analogy of constructions from some sheaves on curves. So in the construction that I described in the talk, I start with associative sheaf of associative algebras over a curve, and there is a similar construction where you can start with sheaf of Lie algebras over a curve, and this will produce for you the solution of the classical Young-Baxter equation.
I see.
So indeed, it seems there's a good reason to view it as an associative analog of the classical Young-Baxter equation.
Okay. Well, thank you very much. That's
Yeah,
very
absolutely.
helpful.
Okay.
All right, so I have to go. I have to take my son to the summer camp now.
Thank you very much. That was really,
Okay.
I thought it was really very, very interesting.
Okay, yeah,
I
thanks.
enjoyed it.
Thanks
Thank you
for the invitation. Yeah,
for
thank
this.
you. Thank you. Bye. It was good
Okay,
to
take
meet you.
care. Bye-bye.
Bye-bye.
Bye.